In this lesson, we're going to take a look at what happens when x goes to infinity. That is, what is the limit when x goes to infinity? So we've seen some situations where x is going to a finite value, like when x goes to 3 from the left. In this function, 1 over x minus 3, what's happening as x approaches 3? It's going down to negative infinity. So the y value is going to infinity there. And if we're coming from the right to 3, then we're coming this way, then that is going to positive infinity. The y value is going to infinity. So watch out. This really means that the limit doesn't exist because this is going down forever. It's unlimited. But when we say there's infinity or negative infinity, it gives us an idea of where it's going. Is infinity a number? Not really. It's a direction. It's a concept. It's unlimited, but it's not a number. Well, what happens when x is going to infinity? Let's think about that. So let's think about these limits. So as x gets larger, as it gets huge, what happens to this value here? Well, we can think about what happens if we put in a really big number here. What if we have like 4 over 1,000? Let's start there. 4 over 1,000. Well, that'd be like 4 over 995. All right, that's a pretty small number. 4 divided by 995. If you were to work that out, that'd be 0.00 something something. Well, what if we put something like 1,000,000 in that x? Or what if we slap some more zeros on it here? What if we go with 1,000,000,000? All right. Well, the bigger that number gets here, this 5 doesn't really matter, right? So if we have 1,000,000,000, 4 divided by 1,000,000,000 is going to be about the same as 4 divided by 1,000,000,000 minus 5. So we can rewrite the limit. So at the limit here, this is really the same as just 4 over x. That 5 doesn't matter because as x goes to infinity, 5 doesn't matter. And what's 4 over 1,000,000, 4 over a billion, 4 over a trillion? Well, this is getting closer to 0, really close to 0, really fast. Okay. Well, what if we have something like this? What if we have 2,000,000 over x cubed minus 2? Well, here again, when we plug in, I'm going to plug in really small numbers, but large but negative, we can say. So when we plug that in there, like we have like negative 1,000,000 cubed. All right. So if you plug in negative 1,000,000 cubed, well, it's going to be a negative number first of all, because when we cube a negative number, it's still negative. And it's going to be a really big negative number. Is this 2 really going to matter? No. So this is the same thing as x going to negative infinity. We can ignore that 2, because if we're talking about 1,000,000 cubed, well, minus 2 is not going to make much of a difference. All right, so let's think about it. It's really kind of like this. And, well, is this number pretty soon going to be bigger than 2,000,000? Yeah. If I plug in 2,000,000 into x, I'd have 2,000,000 over 2,000,000 cubed. Okay? This is a trillion times bigger than this. This is going to have, if you wrote it out, it'll have, 6 times 3 would have 18 zeros. All right? Anyways, so when we divide it, this is much larger. So it doesn't matter how big this thing is because it's fixed. So this is still going to go to 0. Now it's going to 0 from the negative side. Sorry, this should have been a negative there because we're going to negative infinity. But anyways, so but it's still going to 0. So the big idea is this. Key point. All right, so the key point is this. When x becomes very large, either a large positive or a large negative, the other numbers become worthless. All right, it's like this. Imagine that you won $1 trillion in the lottery. So that's this many here, there, and we got 12 zeros there, $1 trillion. All right. The question is, would you care if you lost $100? I'm sorry, $1 first. No, of course you wouldn't lose. Would you care if you lost $100? Oops, just lost $100 bill. Well, that doesn't matter very much because you got a lot more. How about $1,000? You still probably wouldn't care too much if you lost $1,000 because you have a billion thousands. A trillion is 1,000 times a billion. Okay, so you have thousands of billions. Now, would you really care if you lost $1,000,000? Something happened, and you lost $1,000,000. Well, not really. Now that sounds like a lot of money, but a trillion is a million millions. Notice there's twice as many zeros there. Okay, so yeah, so if you lost $1,000,000, that wouldn't matter too much. So the moral of the story is this: when we're finding limits, and as x goes to, not zero actually, as x goes to infinity, that's what we care about, the small terms don't really matter, okay? So we can eliminate them and get a simpler limit is the idea, all right? So if we have this limit here, we got x is going to, let's say, negative infinity, all right? So it's getting really small. Okay, well, it's getting really small. The number is getting very large in absolute value, but it's getting very negative, all right? Well, as this number goes to negative 1,000,000, billion, trillion, does that 4 matter? No, you lost 4. That doesn't really matter. So we can just kind of ignore that. If you have, 5 times a million, is a 7 matter? No, that doesn't really matter. So that limit is the same. It's equivalent to the limit as x goes to negative infinity, still going to the same place, of 3x over negative 5x. Keep that negative with it. That's important. All right. But the 4 and the 7 don't really matter. Now, these two expressions are not equivalent. This first one does not simplify to this, but the limits are going to the same place. All right. So as x gets very large in the negative sense, then they're basically going to act the same. Well, what's going to happen here? Well, we can now use what we've learned about simplifying limits. So that limit is equal to this limit. The limit as x goes to negative infinity still of 3 over negative 5, or we might move that negative upstairs. And we notice there's no x here. So negative 3/5 is negative 3/5, has nothing to do with x. So this is equal to negative 3/5. So we can substitute, but there's nowhere to substitute. So we're done. Make sense? What about this? Here we're going to infinity. Similar idea. You might pause it and give it a try if you want. So when we're going to infinity, that 4 doesn't really matter. That 5 doesn't really matter. Okay? So this is the same as the limit as x goes to infinity of negative x over 3x. All right, and again, those x's cancel, leaving a 1 behind there. And so this is really just the limit as x goes to positive infinity of negative 1 over 3. And that is negative 1/3. All right. So again, when we're going to infinity or negative infinity, those small constants don't really matter. Well, let's look at a few other cases here. When we have not just constants, but we have other variable expressions. All right. So the key here is this: when strategy for finding infinite limits with rational functions. All right. So specifically, we're going to infinity here, and we're talking about rational functions. All right. So we want to eliminate the powers, the lower powers of the numerator and denominator, and then evaluate. Okay. So we want to keep the greatest degree, basically. So here we have an expression going to infinity. Again, that 4 doesn't matter because as x goes to infinity, well, 4 is going to be worthless. Okay, well, what about this x? If we have x squared, well, when we plug in a large number like 1,000,000, we'll have negative 3 times 1,000,000 squared plus 2 times 1,000,000. Okay, now 1,000,000 is pretty big. I wouldn't mind having $1 million. Okay, but when we plug in that, well, this becomes 1,000,000 squared. which is a trillion. All right. So this thing is, negative 3 times a trillion, 12 zeros, if I counted that right, plus 2 times a million. So yes, a million is big, but this thing is a million times bigger than this thing. So this is blowing up a whole lot faster than this is. And so in the end, this, yeah, it's big. Yes, it's growing, but it doesn't matter. It's going to be overtaken really quickly by this power of 2, this x squared. So they're both changing, but in the end, when we get up to large powers of 10 there, or large exponentially large numbers, well, those won't matter. So that 2x really doesn't matter. So we can eliminate that. We can cross out the 2. I know it feels like, oh, we're just cheating here, but we're not. We have a reason for it. And the reason is that at infinitely large numbers, it is overtaken by the larger degree. Okay, so we have this expression because that cancels. No, so we got to think about this limit. We need to write that. Okay, this is your problem solving method. This is your method that you need to show. So now we can cancel it. Well, this x will cancel with one of these. And now we can rewrite this expression as a limit as x goes to infinity of negative 3 over 4, negative 3x, right? One of those x's is still left over there. So that's still there. Well, now what happens when we plug in a large number here? Plug in a million, billion, trillion. We have negative 3 million, negative 3 billion, negative 3 trillion over 4. Well, the top is blowing up. It's blowing up in the negative sense, so it's going to a very big negative number. All right? So this is going to negative infinity. It's blowing up. Okay? So that really means that there is no limit, but it's going in the direction of negative infinity. So it is not limited, technically, but we can say it's going to in that direction to negative infinity. Okay? Well, what about this? What happens as we go to infinity, negative infinity here? Same expression. Again, these cancel. Okay? And so this is the limit as x goes to negative infinity. Okay, of negative 3x squared again over 4x. And again, one of these x's cancels with one of these. We can rewrite. This is the limit as x goes to negative infinity of negative 3x over 4. All right? And again, that goes to infinity. But when we plug it, we're plugging in negative numbers here because this is going to negative infinity. So x become negative a million, negative a billion, negative a trillion. And as we plug in a negative a million in here, it's a negative times a negative, and that's a positive. So this whole number is going to be a positive number. So it's going to positive infinity now. All right? So just going in the other direction. All right? And basically that means it's going to be a slant asymptote. All right? If you've learned about that, we're not going to dive into that quite yet. Right now, that is. Okay? So wherever this is, whatever this graph looks like, if you graph this on your calculator, we'll just mention this here. Okay? It will have an asymptote at negative 2 because that makes the bottom 0 at negative 2. And then it's going to, as you go to the right, it's going to go up to positive infinity. As you go to the left, it's going to go down to negative infinity. Probably more like this. And so what that means is there is a slant asymptote there. And you can find that by dividing the numerator divided by the denominator. Okay? All right. Well, a couple interesting ones here to think about here. All right. Well, if we have like e to a power here, well, remember, if we plug in negative infinity here, that's like e to the negative million. Well, negative that is. All right. So if we have negative a million. All right. Well, the negative and negatives are going to become positive, right? And so this is just e to some positive power, and that's exploding. Okay? So that's getting larger and larger. E to a million, e to a billion. And it's getting really large really fast. Okay? Now, little different example, okay? Let's call this E.2 example. X goes to positive infinity of e to negative x. Well, now we got to think a little bit more carefully, because do you remember what e to the negative second means? Well, that negative power drops it down to the denominator, right? If you have e to the negative 10th, that is 1 over e to the 10th. Okay? So if you plug in, this is going to, x is going to infinity. So we have, like, at one point we'll have a million. Well, this is e to the negative a million. Well, e to the negative million, okay, would mean we have 1 over e to the millionth. All right? 6 zeros there. I scribbled them out. All right? And that would be, this is a very small number, right? 1 over e to a million, you got a huge number on the bottom, and so this would be going to 0. Okay? So if we're going to positive infinity, we'd be going to 0. If we're going to negative infinity, well, we have that canceling there of the negatives. All right? All right? So one more interesting situation. What if we have this square root? Well, first thing we're going to do is we're going to eliminate powers in the sum that are lower than the greatest power, all right? So here we have x to the 10th on top. Now again, we're just going to look at the top separately and the bottom separately. Don't mix them. So just look at the top. So this expression, 9x to the 10th plus 2x to the 5th plus 5, when we get huge, the 5 doesn't matter, okay? And really the 2x to the 5th doesn't matter, okay, because this is a lot bigger, okay? X, a million to the 10th power is a lot bigger than a million to the 5th power, okay? So those, when the x gets gigantic, these don't matter. When x gets gigantic, well, on the bottom, same idea. That one doesn't matter. That x squared doesn't matter because we have an x to the 5th there. X to the 3rd doesn't matter. Okay, it's not going to be worth very much. It's going to be negligible, we say sometimes. So x goes to infinity. Now, don't get rid of this negative 2. That's important, all right? Because that's a factor. We're just getting rid of the terms that have lower degree than the greatest degree, all right? And so negative 12x to the 5th, all right? Now we can clean this up a little bit. We can, first, how about we clean up this square root? Square root of 9 is 3, of course. Let's just keep the other numbers for now. We'll clean them up in a second. Square root of 9 is 3. Square root of x to the 10th, well, when you square root of x to the 10th is x to the 5th, because x to the 5th squared is x to the 10th. All right? Remember, square root is like a half power. So this is like x to the 10th to the half power. Half of 10 is 5. Hopefully you worked on that in the past. All right, so there you have it. Okay, and so what does this become? Well, oh, I forgot my x to the 5th on the bottom. Don't forget that. That's kind of important. It changes everything. So this x to the 5th cancels with that x to the 5th, and we're just left with negative 6 on top divided by negative 12. And that is just 1/2. All right, there you have it. Okay. So when we have these large powers, we got these polynomials with large powers, the small powers can be ignored. All right.